Imagine a vast, empty stage where the universe unfolds. This stage is not just a void, it is a canvas where the drama of the cosmos plays out. Every star, planet and galaxy is an actor in this grand performance. This stage is not empty space. It is a complex, dynamic entity that forms the very foundation of our universe. It is something much more flexible and dynamic. Imagine a fabric that can stretch, bend, and twist. This is the essence of space-time. This stage is space-time, a unified fabric woven from space and time. Space-time is not static. It is a living, breathing entity that responds to the presence of mass and energy. It bends and curves under the influence of mass and energy. This bending and curving is not just a theoretical concept, it has real, observable effects. This curvature is what we experience as gravity. When you drop an apple, it falls to the ground because the Earth's mass has curved the space-time around it. Before Einstein, we imagined gravity as a force acting at a distance. Newton's laws described it as an invisible hand pulling objects together. Now we know it is a consequence of curved space-time. Massive objects like stars and planets warp the fabric of space-time, creating what we perceive as gravitational attraction. Just like a bowling ball placed on a trampoline, the mass of an object creates a dip in the fabric of space-time. Smaller objects move along these curves, following paths dictated by the curvature. Massive objects create a dip in space-time. This dip is not just a visual metaphor, it is a real, measurable phenomenon that affects the motion of everything around it. This curvature dictates how objects move within the fabric. Planets orbit stars, moons orbit planets, and galaxies swirl in a cosmic dance, all guided by the invisible hand of curved space-time. Visualize a trampoline. This trampoline represents space-time. If you place a bowling ball in the center, it creates a dip. This is a simple way to picture how mass curves space-time. Now roll a marble across the trampoline. Instead of traveling in a straight line, the marble will curve around the bowling ball. This is analogous to how gravity works. The Earth orbits the Sun not because of an invisible force, but because it follows the curvature of space-time created by the Sun's mass. The larger the mass, the steeper the curvature, and the stronger the gravitational pull. Time, like space, is affected by gravity. This phenomenon is called gravitational time dilation. Imagine two identical clocks, one placed on the surface of the Earth and the other in space. The clock on Earth, closer to the Earth's mass, will tick slightly slower than the clock in space. This difference arises because gravity is stronger closer to a massive object. This stronger gravity actually slows down time itself. Near extremely massive objects like black holes, this effect becomes much more pronounced. Not just mass, but energy also warps space-time. This concept is fundamental to our understanding of the universe. When we think about gravity, we often imagine it as a force pulling objects together. However, Einstein's theory of general relativity tells us that gravity is actually the warping of space-time caused by mass and energy. Imagine space-time as a flexible fabric. When you place a heavy object on this fabric, it creates a dent or a curve. Similarly, energy can also create these curves in space-time, affecting the motion of objects and even light. Remember Einstein's famous equation E equals mc squared? This equation is not just a mathematical curiosity, it reveals a profound truth about the nature of our universe. It tells us that mass and energy are two sides of the same coin. They are interchangeable, meaning that mass can be converted into energy and vice versa. This principle is the foundation of many modern technologies, including nuclear power and particle physics. This tells us that mass and energy are interchangeable. For instance, in nuclear reactions, a small amount of mass is converted into a large amount of energy. This conversion is what powers our sun and other stars, providing the energy necessary for life on Earth. The relationship between mass and energy also means that energy can influence the curvature of space-time, just like mass does. Where there is energy, there is also a gravitational effect. This means that not only massive objects like planets and stars can warp space-time, but energetic phenomena like light and radiation can as well. This is a crucial insight for understanding the behavior of the universe on both large and small scales. Light, for example, despite having no mass, carries energy and can be bent by gravity. This phenomenon is known as gravitational lensing. When light passes near a massive object, the curvature of space-time caused by the object's mass bends the path of the light. This effect can be observed in the way light from distant stars and galaxies is bent around closer massive objects, creating a lensing effect. This bending of light around massive objects is called gravitational lensing. Gravitational lensing not only bends light, but can also magnify and distort the images of distant objects. This allows astronomers to study objects that would otherwise be too faint or obscured to see. It allows us to observe objects that would otherwise be hidden behind stars or galaxies. By studying the light that has been bent and magnified by gravitational lensing, astronomers can learn more about the distribution of mass in the universe, including the elusive dark matter that does not emit light, but has a gravitational influence. This is because the light from those objects is bent and magnified as it passes through the curved spacetime around massive objects. Gravitational lensing is a powerful tool in modern astronomy, helping us to map the cosmos and understand the fundamental forces that shape our universe. Section 5. Light's curved path. Imagine a distant galaxy emitting light towards Earth. If a massive object like a galaxy cluster lies between us and the distant galaxy, the light's path is not a straight line. The massive object's gravity bends the light, creating a distorted or even multiple images of the distant galaxy. This phenomenon, gravitational lensing, acts like a cosmic magnifying glass, allowing us to observe distant objects that would otherwise be too faint to see. It provides strong evidence for the curvature of spacetime predicted by Einstein's theory. Section 6. Black holes, gravity's extremes. Black holes are regions of spacetime where gravity is so intense that nothing, not even light, can escape. These cosmic phenomena are among the most mysterious and fascinating objects in the universe. They challenge our understanding of physics and push the boundaries of what we know about the cosmos. They are formed when massive stars collapse at the end of their lives, compressing their mass into an incredibly small space. This process often follows a supernova explosion, where the outer layers of the star are ejected into space, leaving behind a dense core. This core continues to collapse under its own gravity, eventually forming a black hole. This creates an infinitely deep well in spacetime. Imagine spacetime as a stretched rubber sheet. A black hole would be like a heavy object placed on this sheet, creating a deep, steep well. Anything that comes too close to this well will be pulled in, unable to escape the immense gravitational pull. The boundary around a black hole beyond which escape is impossible is called the event horizon. This is not a physical surface but rather a point of no return. Once an object crosses this boundary, it cannot escape the black hole's gravitational grip. Once something crosses the event horizon, it is forever trapped within the black hole's grasp. This includes stars, planets, and even light itself. The immense gravitational forces at play ensure that nothing can break free. Time itself slows down drastically near the event horizon and stops completely at the singularity at its center. This phenomenon, known as time dilation, means that an observer far from the black hole would see time passing much more slowly for someone close to the event horizon. At the singularity, the core of the black hole, the laws of physics as we know them cease to function, presenting one of the greatest mysteries in modern science. Section 7. An expanding universe. Our universe is not static but expanding. This means that the fabric of spacetime itself is stretching like a balloon being inflated. This expansion affects the distances between galaxies, causing them to move away from each other over time. The expansion of the universe does not mean that spacetime is being created out of nothing. Instead, it suggests that the distances between points in spacetime are increasing as time progresses. This stretching of spacetime has been happening since the Big Bang. Section 8. Dancing to gravity's tune. Spacetime curvature dictates the motion of celestial objects. Planets orbit stars in curved paths, galaxies cluster together, and light bends around massive objects, all due to the influence of gravity. This curvature is not a flaw, but a fundamental aspect of the universe's fabric. Understanding spacetime curvature is crucial to understanding the universe's evolution. It helps us comprehend the formation of galaxies, the behavior of black holes, and the ultimate fate of the universe itself. Section 9. Conclusion. A universe in motion. Einstein's revolutionary idea of spacetime curvature reshaped our understanding of gravity. It is not a force acting at a distance, but a consequence of the shape of spacetime itself. This curvature affects everything from the ticking of clocks to the paths of light rays. The universe is a dynamic and ever-evolving entity, with its fabric of space-time constantly being shaped and reshaped by the distribution of mass and energy. As we continue to explore the cosmos, understanding space-time curvature will be key to unraveling the universe's deepest mysteries.